Okay, let's review some concepts. First, the electric field. So the strength of an electric field generated by a point charge is equal to the Coulomb constant times the charge on the object producing the field divided by the square of the distance between its object and whatever it is acting on. So the electric field is radially pointing outward from a positive charge and in all directions and towards a negative charge. So the second concept is the electric potential. So the electric potential V in volts at any point in space produced by a point charge Q is given by the expression below. So it is the electric potential energy per unit charge. So to calculate the electric potential, we need K, the Coulomb constant, which is 9 times 10 to the 9th Newton meter square per Coulomb square. So Q is the central charge that creates the potential, and R is the distance from the charge. So you can see that the potential is directly related to the amount of charge. But as you move away from the charge, the potential is going to decrease, inversely proportional to the distance r away from the charge.
Hello, now I'm going to talk about the charges and the fields that they produce using the simulations today. So once you have the simulations up and running, you can notice that there's a list of options and the tools over here on the right-hand side. The charges and the sensors are located down here at the bottom, and a big reset button down here on the bottom right. So let's put a couple of charges out here. And we can see that there's an electric field shown here emanating away from the positive and going into the negative. And the direction of the arrow is the direction that a positive test charge would feel a force if it were placed in that area. So it's going to be repelled by the positive clearly and attracted to the negative. So that's the direction that we get for the electric field. So the magnitude of the electric field is shown here as the brightness of the arrow. So notice that it's getting weaker and darker as you get away from these charges. So you have the option of showing just the direction if you don't actually care to see the magnitude indicated that way, or you could actually turn the whole thing off altogether and just not show it. So the voltage will show you the actual voltage as a red and blue gradient around each of your charges. Now to remember, the voltage is a measure of the amount of the energy that each unit charge would have for the place in that area. So clearly the brighter areas have more energy per unit charge than the darker areas around. And if I add more charges in one area, I'm effectively increasing the amount of charge and increasing the voltage and the resulting field around it. Let me put these charges back off. Okay, so now we are going to take a look at the values now. What does it mean, values? Well, if I put a sensor up here, then it's going to tell me with this arrow the magnitude and the direction of the electric field as a vector. That's changing length as opposed to changing brightness. So again, if I put the electric field back on, and you can see that the direction of the sensor electric field is going to be perfectly aligned with the one that's already displayed. So the value of the magnitude of the electric field is shown as the length of the arrow, which gets quite big as I get closer and closer to each of the charges. Now going away from the positive and going towards the negative. So the values checkbox allows you to turn that on or off, showing the numerical values of the sensor readings of the electric field. So the next is the grid lines. So these grid lines are 10 centimeter grid. So each of these small boxes is 10 centimeter by 10 centimeters. So you could align your charges very nearly perfectly on those grids and be able to make pretty precise measurements without too much difficulty. So in this case, the two charges are separated by 200 centimeters, which is 2 meters away from each other. So if you need to make some measurements that are not on the grid lines, or if you are not using the grid, then you can use the tape measure and be able to measure the distances on the graph pretty precisely. So from the positive charge to the electric field sensor is 148.8 centimeters or so. So you can drop that tape measure off. So this is the accurate potential tool, and it is able to measure the voltage value, just like the voltage shows that. Notice that if we get closer in the voltage, and the voltage is getting bigger and bigger, the amount of energy per unit charge is what the voltage is, and the equipotential or electric potential. And the electric potential, the accurate potential will actually show me the lines by clicking this pencil button. So where all these positions around here on the line have the same amount of the electric potential, 16.7 volts. So they are all connected, and so you can draw these lines at different voltages. And these accurate potential lines behave kind of like the contour lines that you may find on a topographical map, which will connect all the points that have the same elevation above sea level. You can see the contour here. So going back to this, all of these points have the same elevation above 0 voltage. Or as you get closer to the negative charge, you actually have negative voltage. And so the negative charges are more like valleys or holes in the ground in the same topographical analogy. So the positive charges are more like mountain tops. Okay, so if you click the eraser button and click it, clears all of those equipotential lines that you drew. Or if you draw a couple of equipotential lines and you change the charge distribution by putting in another charge, then all of the lines get erased. So be aware of that. So if we have a couple of positive charges, for example, 2 positive charges here, and we draw equipotential lines, this is like kind of like peanut shaped, or if you prefer, these are having 2 peaks at the very top of the mountains, with a saddle in between on a topographical map. So you could create your equipotential lines. So all of these lines connect the dots that have identical values of electric potential. All right, so you'll be using this simulation to examine electric fields and the charges that generate them, and the electric potential that gets created as a result of the charge distribution. And you'll be answering some questions and doing some calculations and predictions, and seeing if your predictions match up with what the simulation shows you. All right, so best of luck to you. Next, I'm going to show you how to find the location where the electric field is 0 when you have 1 positive charge at one location and 1 positive charge meters away from it. Finally, I'm going to illustrate how you can find the location where the electric field is 0 when you have 4 positive charges at one location and 1 negative charge 2 meters away from it.